It requires a restart. Alright, we're gonna restart, right? I'm testing the mic. Does this sound weird to all of you in chat? Are you only hearing it in one ear? Wait, it sounds fine? Wait, what? Okay, let's see. Yeah, 1 year. People are saying there's only 1 year. Yeah. How about now? Is it? Does it sound? Does it sound? Does it sound like, yeah, it's fixed. Awesome. Good. All right, fixed. Great. Okay. So, here we are, day 2 of our abstract algebra course. And I've already mentioned that this is probably not your usual conception of algebra if you're just stopping by. So, not just you. All right, let's put some background lame streamer music on. That deserve to be on Twitch. Okay, great. So I assume that my class is all here, and so I'll begin. Right now we're in chapter 0, class. So you need to just read chapter 0. I gave you a really light, simple homework assignment this time. It's on Canvas. It's 4 problems. One of them's not even a real problem. I'll update you on the exam. Will also be like a not a real exam. It'll just be to test out the exam apparatus and see if it's all working properly. Okay. So we need extremely hard. No. 3A? I don't know. Okay. All right. So I need to start though. Okay. So possibly the one idea in chapter 0 that might be new to folks is the idea of equivalence relations and equivalence classes. Okay, so that's what I'm going to talk about today. And once we are comfortable with that, then we will proceed with the main first topic, group theory. Okay, that's exciting. So first topic, let's do this. What the heck is an equivalence relation? What is the concept of an equivalence relation? Okay, so in math, there come times when we start to equate 2 different objects. We start to think of them as the same in our minds, or equivalent, or for our purposes right now, for the current purposes, these 2 are considered the same. Okay, even though they're not really the same. So that kind of situation happens. For example, it's happened to you when the classic example, keep in mind, is the notion of congruence in geometry class back in high school. 2 triangles were congruent if you can pick one up and then rotate and shift and put it down on the other, and it perfectly lines up. That's what congruent triangles meant. And congruent triangles, I mean, they're the same. But they're not, because one of them's over here and the other one's over there. But like the intrinsic geometry, the sort of geometric properties in one of them, maybe like scalene or being right triangle or some other geometric property, having perimeter 7, I don't know, it's shared for triangles that are congruent to each other. And so in effect, the triangles are the same triangle. Or when you make measurements about the triangle, you get the same results. And so we're tempted to think of them as equivalent, even though they're not literally the same. Okay, so the notion of equivalence relation just makes this whole idea of equating things, even when they're not literally the same, it makes it rigorous. Okay, so that's what it is. So let me give you a definition. Okay, so definition. The sort of sweeping definition of an equivalence relation. Okay. An equivalence relation. Equivalence relation on a set S. Okay, so really it's all of this. This whole phrase is being defined. This is going to look strange at first, but it's like the only way to proceed. So, is a subset inside the product set of pairs of elements in S. So it's a particular collection of pairs in S, ordered pairs, satisfying three properties. One, for any element in the set, that element, comma, itself is always in the relation. Okay, whenever someone has a subset of a product of a S cross S, that's just called a relation. Any subset in the product is called a relation. So that's why the letter R is used. Okay, so we'll do examples. It's not fancy. Okay, so this is whenever you have any element in S, it, comma, itself is always in such a subset, an equivalence relation subset. This is called the reflexive property. I don't care what they're called. I just know them. Okay, next, for any two elements in the set, for any two element, no. Let me write it more directly. If A comma B is related, if A is related to B, if A comma B is in this distinguished subset, then so is okay. Whenever A comma B is in related, then so is B comma A. This is called symmetric. That the relation R is symmetric. And then the last thing is, set theoretic mumbo jumbo. Okay, so the last thing is transitivity. So if AB is in R, and if BC is in R, then AC is in R. Okay? All right. So let me show you how this classic example of congruence fits into this definition of equivalence relation. Okay, so let me just so you're not scared. So I'm supposed to give you a set S and a subset in the product. Okay, so the classic example. In the classic example, S is the set of all triangles. Okay, and R is the following. R is the set of pairs, triangle 1, comma, triangle 2. I'm just going to denote my triangles as little triangle symbols and then put a subscript or something. The S of one triangle, comma, another triangle. R is the collection of pairs of triangles such that triangle 1 is congruent to triangle 2. This is congruent to. Wow, genius. Okay, now you can verify. Every triangle is congruent to itself. Yeah. Okay. If one triangle is congruent to a second, then the second one is congruent to the first. Nice. If you have one triangle that's congruent to a second triangle, and a second triangle congruent to a third, then the first one is congruent to the third. Yeah, it's so clear. Yeah. Okay. So there you go. Congruence is an equivalence relation, and here's your subset that corresponds to it in the sort of rigorous definition. Okay? So, so the ease notation when we have an equivalence relation, we don't actually talk about a subset R in the product. Like in practice, we don't talk about that. We don't like write that. The ease notation, we write like A squiggly line B, for example. We come up with some weird thing that looks like a equal sign. It's sort of more sideways than it is up and down usually. Squiggly line. We write this whenever we mean that this ordered pair is in the relation set. Okay, so instead of writing A comma B inside of R and writing this set theoretic equation down, which is very like fancy looking, this is way more sort of intuitive. A is related to B. That's how we'll say it. A is related to B by the relation R. R is the name of the relation. Okay, relations are all over the place. Okay, so let's investigate this. Relations that don't obey these three properties, it's just too many to even. I mean, just too many. The relations are everywhere. Are all over the place. And don't need to be equivalence. Being an equivalence relation, that's hardcore. Okay, someone asked me right here in the middle of lecture to do the bike. So no, obviously no. Okay, so relations are all over the place. Let's do one. Like let's do one that uses the word related. Like, or the idea of relatedness. Okay, so here's our set S. Here's an example. S is the set of all people. Wow. Okay, what do you mean? All people ever? Yeah, whatever. Just ever. Yeah, ever. Oh, fine. Okay. S is a set of all people, and now I'm going to define for you a subset of the product. Here's a relation. Here's a relation. I'm not saying it's an equivalence relation. I'm just saying it's a subset. Okay, here's a relation. All right? R. R is the set of pairs of people, person number 1, comma person number 2, such that person number 1 is the father of person number 2. That's a concept. It's a relationship. It's a relation among people. Now, all right, chat. Now I'm gonna have chat show up. Okay. So, chat plus class. Is this relation an equivalence relation? Ryan Looney has an interesting comment to make, but more responses coming in. No, that's right. People in the class especially respond, either here or on Discord in the chat if you'd like. Oh, Gath is here. Shout out to Gath. Good, Sheershak, that's right. It's not reflexive, Kappa votes. Absolutely. It's got all kinds of problems, in fact. It's not only that it's not reflexive. That was interesting. Keep this. Okay. It's not that it's not just... Yeah, so I'm not my own father. Failure of reflexivity. Okay, so point number one is messed up. Okay, fantastic. Okay, it's also not at all symmetric. It's definitely not symmetric. If I'm your father, then you're very rarely are you also my father. Not symmetric. Oh, it's just completely garbage relation. Okay. And definitely not transitive either. It could sometimes be transitive. Oh, only in Arkansas, right? Only in Arkansas. You're right, AI. So not transitive. Or transitive only in Arkansas. Right? Good. This is far from an equivalence relation. Okay. So there you go. All right. Next. Now I'm gonna bombard you with examples in mathematics of equivalence relations. All right. So true examples. I showed you the geometry one. But in geometry there was another one. It was similarity. So example number one, similarity in geometry. Like triangle 1 is similar to triangle 2. If there's like a scaling factor that when you scale and you rotate and shift, you get the other one. Okay, so it's just like congruent up to scaling. That notion, two triangles being similar. This is an equivalence relation. This is an equivalence. On the set of triangles. 2. Another one. We say two integers are congruent mod 3. And the way we write it, the replacement for this symbol or congruent symbol, where did the congruent symbol go? Where did I put that? Where is it? Where is it? Right here, this symbol. Yeah. The relationship symbol. Congruent mod 3, written A congruent mod 3. We say two integers are congruent mod 3, or we write the relation like that, A congruent to B mod 3, triple equal sign. If, and here's the rule, if 3 divides A minus B. This is divides. To remind you. Okay? All right. This is a classic equivalence relation on the integers. It's an equivalence relation on Z. Let's verify that really, really fast. Okay, reflexivity. So let's verify it. The verification is usually simple. Okay, so is A related to A? Check. Well, does 3 divide A minus A? Yes. Good. 3 divides 0, of course. All right. So that's reflexive. Reflexive checked. 2. Second property. That's reflexive. 2. Symmetric. Symmetric. If A is congruent to B mod 3, is B congruent to A mod 3? Well, you gotta check the definition. Well, yeah, since if 3 divides A minus B, that's what the first one means, then, you know, then 3 divides B minus A too, because B minus A is the negative of A minus B. But then look, you have to say it like, oh, then A minus B is 3 times K for some K. But then B minus A is 3 times negative K. I.e., yeah, 3 divides B minus A as well. Great. Symmetric. Okay, transitive. Okay. If A is congruent to B mod 3 and B is congruent to C mod 3, well, we're going to ask, is A congruent to C mod 3? Well, I'm just going to unravel these two. Well, then, you know, A minus B is 3 times K for some K in Z. For some K in Z. I'm going fast. And this one means that B minus C is 3 times J for some J in some weird integer J. Okay? But then, if you add these two, you get A minus B plus B minus C. You get A minus C, all on the left-hand side, is then 3K plus 3J, which by the factoring is i.e. A minus C, 3 divides A minus C as well. So you're done. That means that, meaning A is congruent to C mod 3. Done. Okay, so notice how you just have to sort of slowly unravel the definition usually, well, in this example, to deduce whether something isn't formally, logically, whether something is an equivalence relation or not. So congruence, mod a given modulus, like 3, is a classic congruence condition, congruence relation. Next example, linear algebra example. This is called similarity of matrices. This is a reminder from linear algebra. So we're going to let M n by n of R, for example, be the set of n by n matrices with real entries. Square matrices. Then we say M is similar to n. Two matrices are similar if, this is the rule, I'm telling you what this symbol means, if there is an invertible matrix usually it's given the name S for some reason, some invertible matrix S such that S inverse M S equals n. Okay, there's this classic linear algebra equivalence relation, and so you can check. So you should check. Check equivalence relation, and remember that. Yeah, just go ahead and check that. I have faith in you. All right, let me see. All right, good. So that's a classic one. This kind of where you put inverse in front of an element and then you put the same thing without an inverse, that's going to be called conjugation. And it's going to show up again a lot in the group theory part of the course. Okay, so this kind of example is it's going to show up a lot. Okay. Let's see. You can find equivalence relations all over mathematics, and in fact, we're gonna have to become comfortable with them when we talk about quotient groups And this modular arithmetic example is one particular example of that quotient group construction. Okay. But for now, I need to go on to the next topic. So when you have an equivalence relation, you get the notion of an equivalence class. So that's the next thing I want to talk about. Okay, suppose you have a set and suppose it's been equipped with an equivalence relation. And I'm just going to call it tilde. A tilde B. That's what the symbol is for it. And suppose this is an equivalence relation on S. Then, for every element of the set, you get what we call its equivalence class. That's what I'm defining. Its equivalence class, denoted by, well, the book is going to do this. So let's just do it. They'll take A and they'll put some symbols around it. Sometimes they'll take A and put a bar on top of it, or a little, whatever, braces or whatever, like brackets like this. Okay, so denoted this is by definition. By definition, it's the set of all elements in the set such that X is related to A. Okay? X is equivalent to A. So it's the set of all it's the set of all things in the world that are equivalent to you, A. Right? So obviously, notice that the equivalence class of A is never empty. Because it contains the element A. Because it contains A. A is always equivalent to A. So there you go, you get an element. So you get equivalence class is a set, it's a subset of S. It's never an empty subset. Great. So that's the first thing to notice. The second thing that might not be as obvious, but it's pretty obvious, is if two equivalence classes A and B, if two equivalence classes intersect, then they're the same. They can't partially intersect. Then they are equal. Totally equal. There's no partial intersection between two equivalence classes. Okay, they either are disjoint or they're the same. Like there's a 1 or a 0 situation. Okay, let me try to draw a picture here. So maybe this red is A's equivalence class, and yellow is B's. Okay? And let's say they intersected. Okay. Well, if they intersected and they had this element X in it, then on the one hand, we know that A is related to X. We also know that X is related to B, is equivalent to B. And so by the transitivity, or transitivity gives us that A is equivalent to B. All right? But now look, if I give you any other element, Y, let's say in equivalence class called B, B's equivalence class, then Y is automatically also in A's equivalence class. So now, if Y is equivalent to B, then Y is equivalent to A, again by transitivity. And so Y is also in A's equivalence class, and the same argument goes the other way. And so these two sets, equivalence class A and equivalence class B, are the same set. Same other way. So you get these two equivalence classes are the same. All right? So what happens here, what you have to think of mentally, so what's happening pictorially, is your whole set was S, and the relation divides up the set S into islands, these equivalence classes. Your set S gets divided up. They're disjoint subsets. They don't intersect, because if they're different, they're completely different. They have no points in common. Where you have equivalence class of A, and then another one of some other element, X, C, they each have a name. And each one is completely disjoint. Each subset is disjoint from all the others, and their union covers all of S. So every element of S is in exactly one equivalence class. Okay. Yeah, it's like countries. Okay. No, this is abstract algebra. It's going to be harder than discrete math. Okay. All right. So summary. When you have an equivalence relation, you get these chunks of your set where the chunk is like the totality of all things equivalent to a given thing, and therefore the totality of all things equivalent to any other in that equivalence class. So everything, what I want to say here is that, like, each of these pieces, each of these equivalence classes, it's like it's all the triangles that are equivalent to this one over here. All of them. They all fit together in one big grand family called its equivalence class. And that's that one. And then the next chunk of the set is all triangles equivalent to a different triangle, not equivalent to the first one, because otherwise that set would become this chunk. They either snap together or same, or they're completely disjoint. And so what we're doing here is we're sort of blurring our eyes. Mathematically, that's what we're doing. We're taking a set that had, 10,000 pieces. The equivalence relation is giving us a systematic way to blur our vision and to declare that, like, all of these things, this whole piece of the set is now thought of as one islet, one class, one triangle. Even though there's several, if you strictly use equality as your equivalence relation. But if you use congruence, they're all now essentially one triangle, one equivalence class. The other one is a second equivalence class, second triangle. Third, there's infinitely many different kinds of triangles, so this picture is inaccurate for that reason, but it's just a cartoon anyway. Awesome. So when you have an equivalence relation, you get naturally the set divides into equivalence classes. And so now we can actually answer, this last lecture, we ended it with a question, which I don't see anymore. So we can answer one thing. So So I thought this was, if you remember last lecture class, I ended with like a troll question. I said, I thought -2 doesn't exist. Mod 15. Only 13 does. Okay, so you might find some student who has this sort of sense. No, so what happened here is that the equivalence class of -2, that's the set of all numbers in the integers such that n is congruent to -2 mod 15, which is, let me write that very carefully, simply for you. -2, I mean, it goes both ways. So let me write it out for you. It's like -2 is in there. A is always in A's equivalence class. Then there's like -17, I think, and then 13 is in there, and then 28 or something. You know the set. This equivalence class is the same as 13's equivalence class. This is the set of integers such that you're congruent to 13 mod 15. But look at this set. I mean, it's the same exact family. You're going to get 13 in there. You're going to get -2 in there. You're going to get 13 plus 15. You're going to get this plus 15. I don't know what that is. 30, 43, whatever. Yeah? You get that set. But notice, these are literally the same sets, the same chunks of the integers. And if you look at them, it'll be like this equally spaced out collection of integers. 15, exactly 15 apart. Okay, so the student is confused because they're thinking of -2 as an integer. And when we do modular arithmetic, every integer gets replaced. The integer gets replaced with its equivalence class. So they're confusing -2, the number, with -2, the equivalence class. The equivalence class of -2 is not the same as the number -2. So the confusion is simply that A is not, that's not the same. These are apples and oranges. These are not the same. Not this. A versus the equivalence class of A. One of these is an element of the set. The other is a subset of the set. And it's the set of all things that are the same or equivalent to a given thing. Given thing A. All right. So that's the equivalence classes and the equivalence relation, and then how the set gets broken up into equivalence classes discussion. Okay. Question. So all integers in the set of this, in the equivalence class of -2. Yeah. When you so let me try to say that in another way. So very common, a very common math move coming up. Garbage me. It's what streamers have. So math move. Okay, very common math move. It's a running theme. So you might have some set that you start off thinking about. All triangles. Okay. But then you start to think about two congruent triangles as one triangle, one abstract. Let's call it an abstract triangle. Yeah. Okay? You start to clump pieces of this, you start to coagulate the set into chunks. And each chunk you start thinking of as one object. Rather than as 50,000 little objects in a bubble, You just think of the whole thing. We're going to start thinking of the whole chunk as one element in a new set. A set whose elements are like subsets of S. Okay, so you might start with S like this, but then nature will show you how to divide it up into pieces. And it'll start telling, just by nature will just start telling you to start thinking of each piece as just one object. Even though there were several in that sliver, they're all equivalent in our current context. And so you'll start to try to create a new set which is only green dots. But each green dot is, so to speak, worth a whole equivalence class of red dots. And in the red dots for the equivalence class called 13, that dot has several names. They're just different names for the same dot, though. This is also -2. And it's also any other representative in the brackets. Representative of the equivalence class 13. So 28. These are all the same exact dot in this world where we've collapsed the equivalence classes down to single notions, single elements. So this move of taking S and collapsing equivalence classes down to single elements, this is a classic move, and you should think of this as the activity of quotienting. Like division, but for sets. Okay? So that the word quotient should be attached to this procedure. Taking a set that's been partitioned into pieces, maybe coming from an equivalence relation, and then just creating a new set whose elements, whose dots, are entire countries. Good. So that's the real conceptual resolution behind this person's confusion. -2 and 15 and 13, without any other context, those are integers. Those are red dots. But when you work mod 15, the equivalence class of -2 and the equivalence class of 13 are the same element. They're the same object. They're the same subset of S. They are the same equivalence class. That's the resolution of that person's confusion. Maybe they just got more confused. Who knows? But we'll see this so many times that it's going to be absolutely essential that we waste time early on it. Okay, so this is 10:15. This is the pace of our new COVID lifestyle. So class is officially over at this point. I barely got through equivalence classes and their equivalence relations. What I'll do, starting tomorrow, I will begin with the definition of a group, or I'll begin with a discussion of what the heck a group is, and we'll start our sort of long journey across this wonderful subject of group theory. That'll start Friday. Class, you should read chapter 0 and just compare it with what I've just diarrheaed on this iPad. Make sure you verify for yourself that I wasn't lying. What I'll do now is I'll just quickly go into Discord to see if there's anyone in the class who has a question about this material. So I'm going to go into Discord. Anyone who's still around, you can go ahead and ask me a question, and I'll be happy to address it. Okay, Shirshak, I'll get to your redeems. Redeems is for the last 15 minutes of class, which is not even part of class now that we have 45-minute classes. But let's see. Sloth is asking a question. Let's see. And they stop typing. Sloth stops typing. Great. Oh, they're typing again. Everyone. They're typing a whole essay. Oh, there you go. Okay. Oh yeah, that's it. Yeah. Will the reading be listed beforehand? Yeah, absolutely, absolutely. Once I get my life in order. Yeah, 100%. Um, in fact, let me. Um, yeah, 100%. Um, but it's like it might change. Uh, like if I tell you what's gonna happen 3 weeks from now, it might not be true anymore once we get to week number 2.9. So with that caveat, yeah, sure, absolutely, 100%. Chapter 0. This week is chapter 0 only. Just 100%. And next week is like chapters like 1, 2, 3. Some the chapters are they're not as filled with content as they appear to be. They have tons of examples, which is great. The more of the sort of proof theoretical stuff will actually come from me. It seems, based on what I've seen out of this book, I will be the person spewing the harder proofs and the more abstract concepts. But the book will be like filled with examples, and that's the utility, and exercises, which I might sometimes draw from. We're using a book. Oh, Professor Peter is a great luminary. They are a math professor, well, and they should be shouted out time they appear. Check out Professor Peter. There you go. Okay. Complementary algebra, not quite complementary. It's not free, and nor does it is it the no, it's not complementary. It's contemporary. It's a slightly different word, but it means the same thing. Sure. Why not? It's complementary. It's free. It's free when you It's like complimentary breakfast. So the algebra is just free. It's the free algebra. Anyone gets that joke? Free algebra. Joke, but maybe no one. Yeah, no one here. Open source algebra. Yeah, it's open source algebra. Okay. Oh wow, we have textbook AA. Textbook AA command. Awesome. Okay, yeah. Tropical geek. Say. Oh, this. I am confused. This is just. Don't worry. Just, just, just admire the nice colors and pictures. Nova TV Live. Look at this nice. Look at this. It's like I don't know. It's like a butterfly cocoon. That's what we're doing. A very common math move. And now I have to teacher's pet. Oh my god, Professor Peter is teacher's pet today. Awesome. They just redeemed that. Juggle and recorder and shungite. So these were redeemed earlier with channel points. So here's your shungite Shearshak. Here's your shungite inspiration for today. Juggling. Shearshak also wants me to juggle. Go ahead. Okay. Here is juggling. Here we go. Here's your juggling deck. Redeemed it. Channel points, which don't cost any money. Oh. Actually, with this new mic, I don't even know if people can hear me anymore. It's one of those fancy mics that, I don't know, drops off after some amount of. amount of distance. Okay. We have some music. I don't know what to play. Shirshak, you have any requests from me? Oh, good. Thanks. One heart explosion. But Shirshak asked for... Okay, we'll just skip that one. All right, that's fine. All right. So we're going to go on the bike. You're going to review the idea of an equivalence relation and how it divides us up into countries. It's a very divisive, Titanic. Okay. Good job, Crow. Good job. That's the usual effect when faced with an equivalence relation. To collapse the set into equivalence classes thought of as one object now. Great. All right. So this is the last thing I'm going to redeem for degenerates in the chat so that I get my daily exercise in. Equivalence relations. They're all over the place in math. Congruence of triangles. Similarity of matrices, congruence of numbers, quality itself is one of the most trivial equivalence relations. We'll be using them to simplify a large set to little clusters. Concept of quotienting by the equivalence relation. Good, awesome. Oh my God, I think I feel my heart going crazy already. All right, good, done. I did not rip Guru Guhan off at all. Okay. Yeah, thank you, Guru. Yeah. Thank you. Thanks for going easy on me. Okay, Crow also redeemed that. But so that was actually a 2-for-1. Crow, that was also for you. Turns out. Which Dinkin diagram is this? Well, this one. Which Dinkin? Oh, this is. Oh, well, this one's AN. This one's clearly AN. I mean, look at it. I mean, if you look at how I arranged, see, that's AN. Clearly, that's AN. Here you go. There you go. Broken pliers. There you go. All right. Refund my points. Yeah, Crow. It was. It's unclear which one it was for. It was. There was some bookkeeping thing. It turns out it was for you. It was for you, Crow. That one was for you. Now all we need is that Guru is fine with this, and we've solved this problem. It's amazing, genius, 5-head. Guru's not going to complain. Good. All right. So guys, I have a class at 11:30, so I need to go prepare for that, and change my brain from this to a product rule or something. Whatever. Garbage. Autopilot. I gotta make sure my autopilot is working. So yes. What I did was I took the collection of bike redeems and I quotiented so that it became one. I passed to the equivalence class, and so that's what happened here. That's a good point, boring Professor Servant. It was a thematic move that I did. Right? Produce rule. Yeah, produce rule. I'll be doing a lot of produce and produce theoretic garbage coming up in an hour. So but I have to like eat, because when am I gonna eat? So that's right, Professor Peter. Everyone go check out. Oh, Professor Peter is a math professor, does all kinds of cool subjects, streams them, really relaxed settings, really great. You should all check Professor Peter out. Yes, Diado, it will be on Twitch too, yes. But if you like abstract algebra, I don't know. Calc 2 is just, maybe you're bored of Calc 2, so maybe you shouldn't show up. Fingers making a hand, trees making a forest. Very poetic, yeah. No, calc is the best. Very mechanical. No thinking required. Yeah, I think Crow knows me sufficiently well, so that I start to think that this must have been a troll comment meant to trigger me. Good try, Crow. Good try. All right. Very good. I will not comment on your comment, Crow. Good. I will take the high road. I will not fall for that. Very good. All right. Yeah, that's fine. Yeah. Okay. Let's get out of here now. Go. What is this? We have 21 people. Like who's gonna want you folks in their chat? Like who is that? Who's gonna want you guys in their chat? I don't. Melko around? Melko is like the garbage can of science and tech. Everyone just dumps their chat into Melko. So no, there's no Melko. Another garbage pile is the WD-40. Is WD-40 up? Dr. WD-40. No, so we can't. That garbage can is also filled. There's always the chicken garbage can. I don't know. Remember to actually turn off things. Okay, thank you. Okay, thank you. Oh, Tayanyo. Okay. Let me. There you go. Math PhD. Go. Yeah, go troll this person. Don't. Yeah, troll someone else for once here. Get out of here. Start this raid. I gotta turn things off, apparently. I don't know what off. But, yeah, go troll this person. Go. Get out of here. Yeah, go there, Shirshak. Go. Come on. If you don't go, then it'll be like 2 people. Oh, raid now. Yeah, raid. Yeah, go. Okay, then I have to unhost this. Then I have to end my stream.